Standing hundreds of miles from the nearest shoreline, battered by 60-foot waves and hurricane-force winds, sits one of the most complex structures ever conceived by man. This is the offshore oil rig. It isn't just a platform, it is a self-sustaining floating city of steel weighing over 50,000 tons. To build one, engineers must fight against the crushing pressure of the ocean and the corrosive power of salt air. Beneath the surface, these giants reach down through miles of water to tap into reservoirs hidden beneath the Earth's crust. Every square inch of this structure is a marvel of precision engineering, where even a single millimeter of error can lead to a catastrophic failure. Today, we go inside the shipyards and dry docks to see how sand, iron ore, and raw logic are transformed into a titan of the deep. This is the anatomy of an engineering impossibility, from the first weld to the final deep-sea connection. The journey begins in the furnace. To withstand the brutal environment of the open ocean, standard steel isn't enough. Engineers utilize high-strength, low-alloy carbon steel, specifically treated to resist hydrogen-induced cracking and low-temperature brittleness. Massive plates, some over 5 inches thick, are rolled and cut with laser precision. These aren't just flat sheets, they are the building blocks of the pontoons and columns. In specialized fabrication shops, robotic welding arms perform multi-pass welds that are checked via ultrasonic testing and X-ray radiography. Every seam must be perfect. If a microscopic bubble or slag inclusion is trapped inside a weld, the immense pressure of the ocean depths will find it and tear the structure apart. Thousands of tons of steel are shaped into tubular sections, creating the massive legs that will eventually support a structure heavier than an aircraft carrier. This stage is a symphony of heat and heavy metal, where raw fire creates the bones of a giant. In a dry dock the size of 4 football fields, the foundation takes shape. For a semi-submersible rig, this foundation consists of 2 massive hollow holes called pontoons. These act like the feet of the rig. They are designed to be flooded with seawater to sink the rig to a stable depth, or pumped dry to allow it to float. Construction of these pontoons involves an intricate internal honeycomb of bulkheads. This ensures that even if one section is punctured, the rest of the structure remains airtight and buoyant. Engineers install massive ballast pumps and miles of piping inside these corridors. These systems must move thousands of gallons of water per minute to keep the rig level as the center of gravity shifts. It is a delicate balancing act on a massive scale. Once the pontoons are sealed, they are coated in specialized epoxy resins and zinc-based primers to fight off the relentless corrosion of the saltwater environment. With the pontoons finished, the structure begins to rise. Huge vertical columns, often over 50 feet in diameter, are hoisted into place. These columns are the pillars of the city. But the most critical feature of this stage is the moon pool. This is a massive opening in the center of the structure that provides access to the water below. It is the gateway for the drill bit. Designing a moon pool is a hydrodynamic challenge. Designers must account for the sloshing effect, where waves trapped inside the opening can create localized pressure peaks. To counteract this, cofferdams and specialized baffles are installed to break up the water's energy. Meanwhile, inside the columns, elevators and emergency stairwells are fitted. These columns aren't just supports, they are the conduits for power, air, and personnel moving between the dark depths of the hull and the bustling activity of the topside decks. While the hull is built in the dry dock, the topside is manufactured in separate modular blocks. Imagine a Lego set made of 10,000 tons of steel. Each module has a specific function: the power plant, the drilling derrick, the processing facility, and the living quarters. The power plant alone is a marvel, generating enough electricity to power a small city, often using massive gas turbines that run on the very gas the rig extracts. These modules are built with extreme density to save space. Every pipe, cable tray, and ventilation duct is mapped out in 3D software to the millimeter. The living quarters must be blast-proof and pressurized to keep out hazardous gases. They house up to 200 workers in a high-tech dormitory, featuring gyms, cinemas, and industrial kitchens. This is where the human heart of the rig beats, protected from the industrial chaos of the drilling floor by thick firewalls and automated safety systems. This is the most dangerous moment in the entire build, the maiden. The hull is towed out to deeper water and submerged until only the tops of the columns are visible. Then, a massive barge carrying the completed topside deck is floated over the hull. With surgical precision, the ballast pumps in the hull begin to discharge water. The 40,000-ton hull slowly rises out of the ocean, lifting the topside deck off the barge. In this moment, 2 massive structures become one. Welders work around the clock to permanently fuse the deck to the columns. Thousands of electrical connections and piping headers must now be joined. It's like connecting the nervous system of a giant. Once fused, the rig undergoes inclining tests to calculate its exact center of gravity. Everything must be perfectly balanced, because out in the North Sea or the Gulf of Mexico, there is no solid ground to lean on. At the center of the rig sits its primary weapon, the derrick. This steel tower stands over 200 feet above the deck and must support millions of pounds of drill pipe. The top drive, a massive motor assembly, rotates the drill string with incredible torque. But the real engineering happens in the mudroom. To drill through miles of rock, a specialized fluid called drilling mud is pumped down the center of the pipe. This mud cools the drill bit, lubricates the hole, and carries rock cuttings back to the surface. It's also the first line of defense against a blowout. The weight of the mud column provides the hydrostatic pressure needed to keep high-pressure oil and gas from rushing up the well. Sophisticated sensors monitor the mud weight and chemistry every second. On an offshore rig, the derrick isn't just a crane, it's a high-precision geological instrument designed to pierce the Earth's crust with surgical accuracy. How do you keep a 50,000-ton structure from drifting away in a storm? For rigs in shallower water, they are jacked up on legs that rest on the floor. But for deep-water giants, they must be moored. This involves a complex network of suction piles and mooring lines. A suction pile is essentially a massive steel bucket 30 feet wide and 80 feet long, lowered to the seafloor. As the water is pumped out of the bucket, the pressure of the ocean pushes it deep into the silt, creating a permanent rock-solid anchor. These are connected to the rig by miles of chain and polyester rope, some over a foot thick. Alternatively, some rigs use dynamic positioning. This system uses satellite GPS and underwater transponders to control computer-operated thrusters. These thrusters rotate 360 degrees, constantly firing to keep the rig positioned over the wellhead within a margin of error of less than 3 feet, even in a gale. Beneath the rig, sitting on the seafloor, is the most critical piece of safety equipment ever designed, the blowout preventer, or BOP. It is a 5-story tall stack of high-pressure valves and hydraulic rams weighing over 300 tons. Its job is simple but vital. If the well loses control, the BOP must shut it down instantly. It features pipe rams that seal around the drill pipe and blind shear rams, hardened steel blades designed to cut straight through the heavy drill pipe and seal the well completely. The BOP is controlled from the surface via a multiplex system, sending electrical signals through umbilical cables to trigger massive hydraulic accumulators. These accumulators store enough energy to slam the valves shut, even if the rig loses all power. It is the final failsafe, a testament to the philosophy of over-engineering that defines offshore construction. Every BOP is tested every few weeks to ensure it can withstand pressures exceeding 15,000 psi. Before the first drop of oil is ever pumped, the rig must survive its commissioning. Every system is pushed to its absolute limit. Fire pumps are activated, emergency lifeboats are test-launched, and the derrick is loaded with maximum weight. Once certified, the rig is towed to its final destination, a journey that can take weeks. Upon arrival, it is a race against the weather to hook up the mooring lines and connect the riser, the pipe that links the rig to the well on the seafloor. Thousands of sensors are now live, monitoring everything from wave height to structural vibration. This floating city is now ready to serve for 25 years or more. It is a monument to human ingenuity, a masterpiece of steel forged in a shipyard, tested in the elements, and standing as a sentinel over the world's most vital energy reserves. The offshore oil rig is proof that with enough steel, science, and sweat, no environment is off limits. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.